you can performantly generate the same thing every time. And what that means is you can build giant programs.
One thing that is theoretically possible is you could generate straight to PDF. If you don't have support for function calling in a model that you love, you can just add it. If you don't have support for chain of thought, you can add a reasoning step. You can like mock up reasoning by saying you're going to reason in this field and you're going to only use these terms.
You can actually structure the stuff that's inside of the think block.
Hey everyone! Thank you so much for watching another episode of the Weaviate Podcast. I'm super excited to welcome Will Kurt and Cameron Pfeiffer from dottxt.ai. dottxt.ai has really burst onto the AI scene with the creation of Outlines, one of the world's most popular open source libraries for structured outputs with constrained decoding. This is a new approach to achieving structured outputs with LLMs. It's achieving all sorts of applications, things like data extraction and chain of thought, report generation, all sorts of things we'll dive into throughout the episode. And it's such an interesting approach to how you constrain the token sampling to achieve this, all sorts of interesting details to it. Will and Cameron, thank you so much for joining the podcast.
Thanks for having us.
Yeah, thanks for having us.
Awesome. So I'd love to kind of kick off this journey by, I'd love to know how you got into the weeds of this problem. I remember for me, when I first came across this structured outputs thing, I was just like, wow, this is so cool. I'd love to hear your stories as well of how you came to be aware of this.
Yeah, I can start. So, and if you want to talk about like my whole journey to .txt, or do you want to just talk about structured gen stuff, or what are you looking for?
Oh, actually, yeah. Let's do the whole journey.
Okay, I wasn't sure because I saw that in the notes. So, it's relevant. So, I actually had just started working on the AI team at Hex. They make a really cool project, really cool company, great people. And I had known about the co-founders, Remy, Dan, and Brandon, for a while. We're all like really. Weirdly enough, we're all super Bayesian. So I've written a book on Bayesian statistics. Cameron is also like a very like legendary Bayesian, and like the whole company is filled with Bayesian nerds. We don't do Bayesian stuff, but I'm always aware of what these guys are working on. So I remember this paper came out. This I forget the exact title of the paper. It's embarrassing, but the paper they wrote on structured generation. I didn't even know they wrote it. I was reading this paper and I was like, this is one of the smartest things I've seen. In the AI space, there's a lot of hype, a lot of sort of like people just coming up with words for things. And this was a paper that I saw and I was like, wow, this is such a cool concept and solves so many problems. I was working at the time on text to SQL. And I was like, wow, this actually implies you can have guaranteed schema specific SQL. Still an ambition of mine. And I was working on that problem. I thought this is the only real way to solve this. This is so cool. And then I looked at the names of the authors and I was like, of course it's Brandon and Remy. Of course it's them. This is so cool. And they were all at a company called Normal Computing at that time. So I was like, man, this must be a cool place. But I just started Hex. So I was like, I guess that's a missed opportunity for me, but that's all right. I'm really happy with my team. And then a couple months later, they started the startup. They started .txt. They founded it, and I was like, man, those guys are doing some cool stuff. I wish I could be part of that. But again, I was really happy at Hex, and that team was doing great work. And I was just like, hey, you know what? Just not how it worked out. And then one day I got a message, and they're like, hey, Will, we would like you basically to come here and be you for us. Like, write cool things, explain how this stuff works, write code with us. And so I was like, I can't say no. So I was very, very apologetic to the team at Hex, and they were very supportive though because they're a startup, so they understand. And I joined on, and I was employee number 2, and it was very cool to sort of be founding engineer working on solving all kinds of hard problems. And that's how I ended up at .txt.
Oh, that's so cool. I've heard a lot of normal computing now, and that's it seems like some really interesting stuff. And and Hex also the data visualization. I think that maybe we could touch on that when we're talking about report generation. I think there was some awesome.
It was cool to come from the like at Hex. You're on the entire application side, so it was actually a really helpful experience to get coming into .txt because Cameron and I. The fun part about this job is we're both kind of discovering exactly how you do these things, how these tools are used, and so having that experience at Hex was actually super valuable to me because I had already been on kind of the user end of LLMs and thinking about them from that side. So getting deeper into the machinery was a lot of fun. It's still a lot of fun.
That's super cool. Cameron, sort of pass you the hot potato. What's your story
Sure.
that led you to dottxt.ai?
At the start of my PhD, I started working on the probabilistic programming language in Julia called Turing.jl. And that kind of put me in like the broader probabilistic programming language community. And Remy has been like in the probabilistic programming space for a really long time. So we like kind of like started following each other on Twitter. And basically I remember seeing the like first tweet about outlines when it came out. I was like, this is cool. Like this is really cool and simple, and I didn't think too much of it. I was just like, okay, that's cool. I know that there's that thing happening. And I was an economist at the time, so this was like kind of cool and interesting, but not, like it wasn't going to change my life. And then I was wrapping up my postdoc, and Remy posted something about how they're looking for a developer relations person in San Francisco. And I was like, oh, I live in San Francisco. That seems cool. So I responded, yeah, I'll submit an application. And then I forgot. And then he replied with the eyes emoji. So I was like, okay, I actually have to go submit an application. And I love the team. Like everyone's super smart. I talked to Will, and Will is like very excited about like all the cool stuff that we do. And then I was also really excited, very excited about all the cool stuff we do. So yeah, I joined, and it's been like excellent. Like I get to do all this like very cool, super interesting stuff that, like as Will said, is like extremely novel. Like, I think Will and I kind of sit down like every week or so, and we're like, oh yeah, like there's like maybe 10 or 15 people who are doing this thing, and we think it's like kind of an important part of like the future of AI. And yeah, so that's kind of how I made it a .txt.
Yeah, I couldn't agree more about the importance of this on the future of AI. I think this structured outputs thing, and yeah, I can't, hearing this Bayesian background and your background, Cameron, I can't wait to really go deep into these things. But if you don't mind, if we could kind of start by just explaining what structured outputs are, maybe for developers who are a little new to the concept, just maybe like giving the little like overview of what it is. And
Yeah, I mean, do you want to take that, Cameron, or I'll go. So structured outputs.
You're the best at the basics.
Oh, am I? I sort of have. I have I have like multiple views of this. I have like my extreme like fantasy weird view of this, which we can hopefully get to.
Don't do the like infinite set to infinite.
Okay, we won't start with the infinite
thing.
sets.
Yeah.
Okay, there's this version of this that's very cool. So for the non like dream version of this, which there is, structured outputs just means that you guarantee the format that your LLM is producing, which is like the most obvious case of this is JSON. If you want reliable JSON out of an LLM, then that's what you need structured outputs for. And in particular, structured generation is about how we do that, which is actually at the logit level. So we're actually controlling during inference which logits are allowed to be used based on the structure that you want to generate. And I always like pointing out that structure isn't just JSON. It's really everything has some structure. Like when you write an email, there's a format to that you have. When you tweet, there's a format to that. LinkedIn posts have a format. Even just things like zero-shot classifiers, people often forget. If you want to quickly build like a zero-shot classifier that just says like hot dog, not hot dog, which is an example we actually used in a recent course, those things require some structure. And so we are able to guarantee that the model outputs that. You can define it using a regular expression or a variety of other tools. And so it's really essential to building out applications with LLMs, in our opinion, at least.
Yeah, amazing. So maybe we could just kind of roll into these new applications. I think, probably the first, like you say, like if you're building a classifier, just the fact that it will always output the classes instead of making up a class or saying, sure, I can help you with that, and then giving you the class, or, if you're doing like float valued outputs, Boolean valued output, all this kind of thing. But I think there are also just like all these completely new applications, like I really like kind of like the ETL thing. Like I know, Cameron, you have an example that's doing this self-evolving knowledge graphs thing, and say taking a paragraph of text and extracting out these like entity relation tail tuples. That's like one kind of thing you can do with structured outputs that just would have been really hard to do otherwise. And yeah, Will, you opened up with like the text to SQL, maybe a bit more of an intense example, but I think if we could just kind of start by talking about this, like these totally new applications now that we can structure our outputs reliably.
Sure. So I think My general sense of the application space is that people are still trying to figure out what is interesting and useful. And so for our use case, we've seen people do a lot of interesting stuff with knowledge graphs. Like, you mentioned the source target relationship thing. I have an example on, we can put it in the show notes. It's the self-expansion repo. We have and that allows you to kind of build, use language models to construct structured knowledge graphs that you can query, in a principled way. And you can determine your ontology in advance. I don't want to go too far into knowledge graph stuff, but you can dictate the structure of your graph and allow the model to fill it out without having to be too heavy-handed about prompting or anything. You can just say, please build me this knowledge graph. This is what I expect to see. Give me those tuples. You can use that kind of stuff for all sorts of things like research. There's some legal stuff I've talked to people about, but I don't know exactly what the status of that is. And then, of course, there's misc data annotation. That's actually a very common one. We have somebody who submitted a cookbook to us about annotating data for Wikipedia. So you can get images, you just feed an image to the language model. You say, what's in here? What are suggested captions? Just identify agents or actors inside of the image, describe what they're doing, what they look like, etc. And that's actually a very easy and flexible way to do, reliable data annotation at scale in a flexible way, as opposed to manually trained classifiers, in kind of a standard ML approach that are a lot less flexible. So yeah, there's just lots of cool, interesting.
Yeah, and some other things we've done, which I really find are cool, just even for information extraction, imagine you want to get phone numbers out of a data set, but your users have the phone numbers in all kinds of different formats, but you want them in a consistent output, which is if you're doing that, often things like phone numbers, think, well, I can write a regex for myself and write a processor in 5 minutes. Why would I use an LLM? But when you think, okay, well, how many different formats do people write phone numbers in? Now, if that's your task, you're going to start going, oh, this is a pain. I have to do all of these fuzzy matches. But LLMs are good at pulling it out. But then with structured gen, not only can you guarantee you get just a phone number out if you want, you can say, this is the format I want it to be in. And all the experiments we've run, all sort of demos we've made around this, it works. Even with very small models, I've been impressed. And then sort of the higher level of abstraction from that, I think, is function calling. We built out a demo for Hugging Face when they released their small model that mapped natural language to basically mocked up application calls. So you actually would get a function call from the model saying I'd say, order me Starbucks with 2 cups of coffee, and it would generate a correct function call with that, even on a very small model. So being able to do that stuff is really the function calling capabilities. And the cool thing is you can do this with any model. It's worth highlighting that. If it's an open model, any open model, you can, if you don't have support for function calling in a model that you love, you can just add it. If you don't have support for chain of thought, you can add a reasoning step. You can mock up reasoning by saying you're going to reason in this field and you're going to only use these terms. You have all kinds of cool fine-grained control that you normally wouldn't even think about having that ability to control that. And you can take any model you want and build out that functionality very quickly. So it's a lot of fun and also very powerful. It's more than just fun.
Yeah, I love that nugget about function calling with smaller models. I hadn't heard that before. That's a really cool one. If you don't mind if I kind of unpack the metadata extraction one, I do have one question about this where it's is there first an inference, it just kind of maybe is a question about kind of what are you seeing? How are you seeing people using this? If I'm parsing, say, SEC 10K documents, am I always extracting the same out? I have my schema, of course, for my data, it's my index, and I already have a schema. Or is there an inference where first it looks at the image and then it pulls out the schema and then it are these schemas are you seeing them being rigid? It's already a defined schema in a database, or is there's sort of an inference step first and then an extraction? Because I just imagine each page of the SEC 10K could have a different structure, or yes, I get
Yeah. So typically when you're working in problems extracting stuff from 10Ks, you know exactly what you want before you go in, because you have a business case, right? You want to see you want these particular financial metrics. You want to try and summarize discussion in a structured way, positive sentiment, negative sentiment, etc. And so typically for most problems where you would be using structure generation, you want to know exactly how you're going to program the output. So if you fix the schema in advance, you can write code that says, I know that I will always have a sentiment field. I'll always have this stuff. If you do the inference step that you're just kind of describing, where you basically have the model look at your data set and propose a JSON schema and use that to generate the output, it's not always super clear what you're going to get out of it. I do expect some people to start trying this, the inference step to generate a schema and then use that schema to process the data. But I don't think I've seen a strong use case yet. But I'm still super interested. Like, I love the idea of just like proposing a JSON schema and then just like letting the model figure out, just describe to itself how it's supposed to propose the data and then write code that uses that output schema or whatever. Yeah.
Yeah, I think that's an area where we definitely see that there's sort of more work to be done as far as like getting these things usable quickly. So like inferring, that would be amazing to be able to just accurately and reliably infer the structure you want from a problem, from the problem itself. And I like to think we'll eventually get there. I've experimented with like little cases of like, okay, I'm asking a question, I'll ask a more powerful model, like, what do you think the regex match for this is? And then plug that into outlines. And it's really kind of like, it's getting there. And the other thing I do want to mention, which is kind of fun in some of the experiments we've done, is you can like define the structure on the fly. Like for some of the function calling work I've done, you actually like the model, like you just slurp in the function definition and generate the structure. Like you're not doing it, like you're writing code that generates structure for you. So there is kind of an intermediary between like, I've defined this rigid thing, I spent all afternoon thinking about it, versus like I've come up with a pattern for generating these things. So these are definitely more advanced use cases. Like I think it's always a challenge. Like Cameron and I are always doing these really outrageous things that are kind of at the edge of what we can do. And then we're like, oh yeah, we have to tell people, if you want JSON, you can use this.
Yeah. You want a hot dog, not hot dog classifier. And that's like the thing that we can do too. Very easily. Yeah.
Yeah, awesome. It's like kind of like we're working on like database agents, like kind of layer around data, like agents that help you use databases. And one thing that really fascinates me is that first step where you have to design a schema for your database. Like I feel like there could be more we do where it could look at your data and propose, I've seen your data. Maybe here's a schema that makes sense for you, and yeah, things like that really interest me a lot. So maybe kind of just unpacking these things. Will, you had touched on using structured outputs for reasoning. I'd really love to kind of unpack. I know. Oh yeah.
Yeah. So no, it's a neat topic, and it's something that I actually bumped into by accident. And this is another topic we'll talk about too, I'm sure. When I was originally joined dottxt, a rumor that had been going around for a while is that structured outputs ultimately hurt the results, the quality of your output. So when I joined dottxt, I actually personally didn't know if that was true or not. The leadership was very confident that it wasn't true, but I was like, I had people when I joined saying like, does this work? Anyway, I my first thing I did was set up evaluations to kind of test this on like GSM8K. And I was controlling, and it's a very standard reasoning step in GSM8K, which is where the model thinks about how to answer it, then it answers. And in my first pass at this, I was like, oh, like it's close, but it's not quite performing as well as the baseline, which is not structured. So I was like, that's a bummer. But then I realized I had a very tight constraint on how many characters the model could think for. And I actually looked at when it was reasoning unstructured and was like, oh, it actually tends to be using many more characters, and I'm letting it. So by simply changing how many characters it could think for, the performance like exceeded what was the benchmark. So not only did we not lose performance, we were actually getting better results. And it was really exciting, but it was this realization of, oh, you actually can define what the reasoning process looks for, like how many characters. And the interesting thing is, like, even though we did initially lose performance in that first round, it was much faster because the model wasn't taking more time. So this is an interesting case where, okay, like let's say you want a reasoning step and you actually really have hard constraints on token usage. Like I want this to reason, but I only want it to use so many tokens. I need this to go very fast. You do have that knob, which you don't, like normally you wouldn't even think about that when working with LLMs, that you can tell it how much to think for. Cameron and I have some like wild ideas about like, Cameron's done some really cool stuff. I want him to talk about. We haven't like published this yet, so I don't think it's secret. It's sort of just like experiments we're working on. But like you can mess with that. So in my GSM8K example, I allow it only like sort of basic letters, numbers, punctuation, and only the punctuation necessary for doing math, like division, multiplication, addition, and subtraction. And I haven't run this experiment, but in theory, I'm like, well, if you remove the division operator from problems that require division, how will the model perform on division? Like, can you systemically make it do worse by not letting it think the right words? And it's interesting whatever the result is. I know, Cameron, you've done some other experiments in this space, so I'd love for you to chat about that because it's very cool.
So one of the things that we started tinkering with was R1. So R1 was kind of like the first like real open reasoning model. And, reasoning models have this problem with structured text where the very important part about reasoning model is they open with a think tag and then they fill out some kind of free-form text where they're like, I understand the problem to be this, but wait, let me think about this, blah, blah, blah. And then there's the closing think tag and then some response. When you want structured output, if you just structure everything in a dumb way, then you don't get the reasoning step. You just get the output, and then it's not clear why you're actually using a reasoning model in the first place. So there's actually not, I have like a GitHub gist about how to do this, but you can leave the think block mostly untouched and then just output structure at the end of the reasoning block. And an additional part of this that's very interesting is you can actually structure the stuff that's inside of the think block. So for example, I had this like very simple example where I didn't allow the model to say anything with an R in it. So no R, no lowercase or capital R. And then I asked it, roses are red, violets are blue. Are roses red? And it freaks out. It doesn't know what's going on. It's like, I'm sorry, I think that it's blue. I don't know. And so you can do all kinds of stuff like this. You can enforce a particular format. You can have only allowed words, disallowed words. There is even an example I tried where on the GSM8K benchmarks, I didn't let it use numbers. And when you don't let it use numbers, it actually uses Unicode characters, superscript characters for exponents, basically, like 1/2, superscript 2, things like that. And it doesn't behave very well, as you might imagine. But there's all kinds of stuff you can do to structure that reasoning block and then also get some kind of structured output that you would normally use in your application. So you can get all kinds of you can really play with reasoning models quite a bit. And I don't think we're still kind of scratching the surface there, I think.
Well, that's absolutely amazing. I guess I've been so sort of limited in my thinking about this, where I'm mostly thinking it's just like, hey, I want these 3 string valued outputs with these different names, or like I want a string and 2 floats, not like I could take away the R's. And I don't know if you guys were taught to write, I was always taught to write you give your introduction, then you give kind of like your high level of 3 evidence. So, and then you have the 3 paragraphs and the counter argument and the conclusion. So yeah, I'm thinking about wow, you could really structure reasoning in a really particular way. And that's amazing. I'd never thought about that before. Yeah, which actually, so this is kind of the next question I wanted to ask, and we'll definitely come back to the let me speak freely and the distribution mismatch. I think that's going to be a great topic. But the next topic that I think flows from this one really nicely is Cameron, you have a blog post that's about holiday gifts and about report generation. And what I really love about this is how it shows how you can take structured outputs and flow it into sort of HTML component. Like you have a JavaScript component, and because you already put H1, H3 tags, and then it creates this structure. Yeah, so if you wouldn't mind telling the story of the holiday gifts.
Sure. The holiday gift thing, we were trying to think of what's a holiday example thing we can write. I was like, well, I'm terrible at giving gifts, really bad. And I'm surrounded by people who are great gift givers. And I was like, okay, I need to compete somehow. And so I turned to AI, and it doesn't work that well. Spoiler alert, it's not very good at giving thoughtful gifts. But basically what I built was a super simple web app, and you just have a text box, you fill it out, you type in some information about the person. So you basically just be like, oh yeah, my brother likes ultra marathons and suffering, and Russian novelists, things like that. And then it'll pass it to the model, and the model has a very specific output that fills out a report, basically, that says, this is my understanding of this person. This is a style of gifts that we might want to provide, and then a list of gifts. And so it'll go through and it'll create divs, basically, for each gift with a name of the gift, where you can expect to find it, a description of the gift, and then why you think it's a good idea. And then I also added a little field for what you should write on the gift card. and it's not good. Like, don't use those. It's very obvious that it was written by a language model. But that was like kind of an example of how you can basically just make like you don't really need a backend. Like, really, all you need to do is just like pipe language model stuff into, or prompts into your language model, and then render web pages directly from that, more or less. So that was a fun project, a little dorky, but it was a fun project to think about kind of the intersection of web and structured text.
The last part about the you don't need a backend now has me trying to think about that part a little more. And so like I'm always going to be generating my websites on the fly. Like this kind of, I think this is sort of related. Bob really loves this idea of like it's like video games that are sort of rendered on the fly. Like the video game doesn't actually exist, but as you click left in the game, it renders it. And is this kind of the same idea, you think? Like yeah, sorry to double click on that one particularly, but what does it mean to use this instead of a backend?
So this is like a mixed backend, right? So this is like, I generally propose the structure, and then I have like some super simple stuff that'll just like pass like a text box to the language model. And then it has a rough shape that it's expected to create. The thing you're kind of describing, where games are generated on the fly, is basically UI generation, which is something that we've talked about a little bit, but we haven't really gotten into that much. There's, OpenAI has some super simple examples of generating raw HTML, because you can just, represent that as JSON, div, content, span, blah, blah, blah. But I would love to see more like dynamically generated UI.
And we do have some kind of ambitious projects in mind. They're not quite there, and this would require our internal version of the product that we have. But like one thing that is theoretically possible is you could generate straight to PDF, because PDF is a text document ultimately with its own grammar. So like, and you think as a developer, normally these are things we don't even think about automating with AI. We think about AI writing code when you think about automation, but I'm like, there's a whole nother layer where like, as a developer, I think we've all written like I have to generate a PDF at the end of this, and it's annoying, and you have to look at the PDF spec, and you find a good library, and it's buggy. Like, what if the model could just reliably, literally output to file name.pdf, and it's a valid PDF document, and we can guarantee that. Like, we have the ability to make sure that's true. And the other example is a PowerPoint presentation. Like, there is a standard markup, and it's like without even the intermediate step. It's not even like go to JavaScript, JSON, and then transform it to this. It's like, no, like literally dump it to a file called something.ppt directly from the LLM, and it's a valid PowerPoint. And it's like, when you think of it, like I said, we have this framework for thinking about AI automation where it's like, oh, AI will write the code for us. And it's like, no, but AI can also like, we can just skip steps because we can have the model generate, especially when you combine LLMs with this structured generation.
Oh, amazing. I think also with the 4.0 with the images, it's becoming so clear that it's going to be really great at generating images. And so I love that PowerPoint example, because it could do all these parts, even add like little visuals to it.
Oh yeah, wow. That's actually really awesome. I really want to build this thing.
Yeah, it would save a lot of time. Awesome. So those are kind of the topics I wanted to cover on sort of the applications of it. I definitely wanted to like maybe just quickly, I think we've already covered this pretty heavily, but there's this one other topic about like I was amazed to find that this paper actually exists about multitask inference, because I've heard this is a concern that some of we've been discussing within our team, is like, hey, should we really be doing all, like, because with the structured output, let's say it's writing a summary of the document as well as like a simulated question, and then it's also like extracting the title or something. It's like, should we really be doing all these things in one inference? And so have you ever heard anyone kind of push back on let's do all these things with one inference? The paper that I found says that, yes, it is better to do all these things with one inference.
I've empirically found that it is. Weirdly enough, I had a demo I did where I had complaints processing data. And it was funny because I had a task where you extract the department the complaint's about. Very simple, like, and then there's another one where you process the whole document. You grab the department, summary of the complaint, order number. And weirdly enough, it did, at least in this one example, it actually performed better when I had to do everything. So it's like, I've at least a little bit seen that. And it's a kind of exciting thing when we think about LLMs. Like I said, it's sort of like a new way of thinking about, like, in software, normally you would, of course, break it down into small pieces. You would never think, let's try to do it in one pass. You wouldn't have one function that does that. But with LLMs, it does sort of look like there's a lot of benefits to just saying, like, do it all.
Yeah. I've had the same experience. I had another example of the SEC, extraction thing. And I started adding all kinds of stuff. I was like key observations, like sentiment, like reasoning, reflection, blah, blah, blah. And so when you do this, you're forcing the model to start contextualizing itself. So the farther it gets as it prints out the actual JSON, can look at the stuff that it's already said, and it can kind of reinforce it in the same way that chain of thought works. So I like totally agree. Anytime I do any kind of language model call, I basically want to put a thoughtful amount of things inside of the JSON that I get back. And you can use this because you can trick the model to do better because it understands the problem structure a lot better. And it's cheaper because you don't have to do the pre-fill step every time. I don't want to do 5 calls when I could just do 1 call. And if there's no material change in performance, then I don't mind.
Yeah, I think that last point is definitely what sells it the most, is that, it's going to be faster to do the 5 things at once. And then that pre-fill, super interesting stuff. Awesome. So, I did pretty well in my computer science classes, but formal languages and automata theory was one of the hardest ones for me. I didn't really get it that well, honestly. So if we could dive in now into, how does this work?
Yeah, I'd be happy to. This is like I love formal languages. So I used to be a programming language theory nerd long before I got into even machine learning. So, so the basic idea is everything is driven by a regular expression under the hood, essentially. And any regular expression can be mapped to like a finite state machine, which you probably remember those little graphs. And then once you have this finite state machine, it's actually very fast to keep track of where you are as the regular expression goes and which so you can imagine the finite state machine, it would be like what you've observed, the current state you're in, and then what's allowable tokens from that state. It's a little more subtle than that, actually. Is what I'm describing is what would be normally considered a non-deterministic finite automata, which is still defined by a finite state machine. Technically, Outlines uses a deterministic finite automata. There's only one transition from state, which means there's a lot of states. But that's like kind of way in the details. It's cool details, but it's way into it. But basically, because it's very fast to move around to keep track of where you are in the generation process, you always know what's allowed at any given point given the previous things you've seen, and then you just mask the tokens that aren't allowed, and you're basically computing a conditional probability where you're saying, okay, given what's allowed, that's what I produce. And then just a tiny bit more of theory, because I always feel like someone's going to pay attention and think that we don't know what we're doing. We'll talk about, especially in our commercial product, context-free grammar support. And if you're into formal languages, you say, well, context-free grammars are strictly like more powerful than regular expressions. How can you represent a context-free grammar as a regular expression? And the answer is you can by just limiting recursion depth. It's very similar to how any, not that everyone knows how a DAG works, but if you have cycles in your graph, you can convert it to a directed acyclic graph just by saying up to a certain number of repeating cycles, you can unroll it. Very similar principle to how you can take a context-free grammar and represent it as basically a finite state machine, NFA, DFA. So that's the basics of it. What it means is that the cost at inference is very, very, very low. There's almost no, like for anyone that's running these applications at home, you probably won't notice the difference in inference time at all. And even if you are running like a production inference server, and you're using, especially if you were to use our commercial product, you're talking microseconds of like very, very minimal overhead, which is a huge win because these people really care about that speed. So whether you're a user of the open source product and you kind of have like regular human user requirements for inference time, you won't notice it. And but if you're in like a super high performing production team where every microsecond counts, you also will not really notice the inference cost, which is like a huge win of this technology.
Yeah, amazing. And that was kind of one of the counterintuitive things from when I always thought, okay, you're computing all these what's allowed, what's not allowed. Surely that there's some overhead to that. But then, so I think there was one other thing I was learning about when I was reading the blog post on dottxt.ai, which is you also like don't need to compute these because if it's not allowed, you don't even need to transform it into a vector at the last stage of sort of the transformer inference.
Yeah, there is some work to be done. I don't know how much the results can be made public, but you actually can theoretically, since you know what doesn't need to be done, you actually can trim out computation in the neural network itself because you know certain paths don't ever actually have to be computed. So you can I think it's not, if I remember, and again, I don't know all the details, but it's not as huge a win as you would hope for the amount of kind of work, because the logistics of actually performing that sort of cleanup of what doesn't need to be computed costs something too, right? So, but it's there. And then the other thing, which we did write a blog post about and are working on a bit internally, is coalescence, which is another huge performance potential gain. If there's think about JSON. What's the first token of JSON going to have to be? It's going to have to involve a curly brace and a quote. Why are you generating that? If you know what you're going to get, why bother? Structures have lots of redundancies in them inherently. That's why it's structured. I think you could actually argue that's what makes something structured, is it has certain redundant known information. You can basically fast forward through that. And we have an article we wrote about this theoretically, and we are working on it now internally, actually implementing this, but it leads to like significant speed ups. Like we're talking like 2 or 3 times or more if you have like a problem like JSON, where you have very well defined, very high amount of structure in the output of the data. So that's another place where there's really cool possibilities of performance improvements.
Oh, amazing. Yeah. Awesome. So I think maybe this would transition perfectly into kind of like another question, like an adjacent question to this that I wanted to ask about is, like, at Weaviate, we're using outlines with vLLM. And so I was just curious, like, how low level do you go with implementing this finite state machine kind of stuff? Is it is it just at like kind of like a token decoding level, or do you go into CUDA kernels, or yeah, I guess just like my question is kind of like broadly, like, how does this get packaged with these sort of like inference engines?
Yeah, I'm not following the vLLM stuff too closely. I'm aware of like the general landscape. So for the longest time, and I think a lot of the vLLM stuff that people use when they ask for constrained decoding, by default, it routes to X grammar if you don't have a very complicated schema. If you need like lots of like, kind of mildly complicated features like inline regular expressions and stuff, they'll fall back to outlines. vLLM, I think, I don't remember as of which version, uses a pretty old version of outlines back when everything was written in Python. We don't have that anymore. We ripped out the entire backend of outlines and put it in a Rust library called outlines core. And outlines core has a very simple interface. You basically construct a vocabulary, which is a fast version of your tokenizer, basically, and then you construct an index. And the index is this, this finite state machine that says, okay, I've seen curly brace quote. My first key is dog. I must output the text dog. Those are the only permissible tokens, or tokens that combine to form dog.
Yeah, outlines core is actually a great place to look if you want to understand what's actually happening, because it completely removes. I actually have a personal project I was working on where I wanted to demonstrate structure gen, but I actually didn't want to use outlines, so I needed to get into the tokens. And I actually, for an initial version of it, used outlines core because you can actually control at the logit level, like you can step through the process. And if you're writing it yourself from scratch, it's not going to be super performant, but not because of outlines, but because of your own sort of implementation. But basically, you get the logit mask from it. Like, you get the logits that are allowed, and you can build a mask, and then you block out those logits, resample the probability. So outlines, the library does that part for you. Outlines core is just keeping track of that state machine and making sure that you're only at any given point what's admissible and what's not. And having built like something from nothing in this, it's actually cool. So it's a great way to get a sense of actually how it's working. And as Cameron said, it's a super simple API. Like, once you actually see it, you're like, oh wow, this is actually like awesome.
It's like 2 lines. You when you're masking it, when you're masking your logit layer, you just pass it as a function to your logit processor, and the logit processor will just turn stuff off. That's it. And so vLLM 1.0 is changing a lot of the internal stuff. We're very excited about. I love vLLM. We're big vLLM fans. So if you're not using vLLM, you probably should. It's very good. But 1.0 is changing a lot of the internals about how structured generation works. And that would probably include updates to the outlines backend that goes into vLLM. So you'd start getting more magic. Even though vLLM is already magic. God, it's such good software.
Yeah. That's what I hope I can ask the right questions. My depth of this goes as far as that logits processor and
You know what? That's as far as you need to go. You don't need too much harder than that. You have a bunch of token probabilities. You say, okay, I don't need those probabilities. They go away, and then you sample the only appropriate ones left. Easy peasy.
Awesome. So, but I guess I just wanted to kind of ask about, that kind of maybe you guys being closer to it than I am. Like, I know about vLLM. I think kind of SG-Lang is like another type of thing, and then you've got like the Hugging Face TGI. I think is a different thing, and I think NVIDIA has like Triton servers. So maybe if you wouldn't mind just like kind of explaining what that whole landscape looks like, because you have like this kind of like inference engine. I'm not even really certain what I understand it's like continuous batching, stuff like that, but I honestly don't even really understand that layer that well.
Yeah, I can do that one if you like, Will.
Yeah, sure. I'll be happy. I think you're more in the weeds in this stuff than I am, so that's great.
Okay. So Outlines pops up in quite a few places. For the most part, I would say vLLM is definitely the easiest way to access it. I don't actually know the status of TGI, so that's the text generation interface from Hugging Face. I know that if you're using Outlines as a front end, you can use TGI, you can structure TGI outputs. I haven't really played with that most of the time. I either use transformers or I use vLLM. Llama CPP has its own structured output backend that's kind of this like grammar thing. You can use Llama CPP through Outlines and do the logit masking on, by taking the logit output from Llama CPP. So, the mixed inference support for various backends, I would say is, kind of varying. I expect over time to see much more structured output across the board. So Olama, for example, recently implemented this, I don't know, maybe this was a month or two ago, the structured output for using Llama CPP's structure support. And then they're also writing their own inference engine in Go, which presumably is going to include some structured output, and hopefully they would use Outlines as Rust Outlines core so that they can do all that stuff for cheap. And then the last thing you mentioned is kind of this NVIDIA like microcompute type stuff. Those are called NIM, which is the NVIDIA Inference something. I'll look up whatever NIM is. Hold on.
Let me read. Microservice.
Yeah. No, NVIDIA Inference Microservice is probably what it is. Right?
I think it's even microservices, and they're pretty particular about not adding the S to the end of it because it's already contained in the microservices.
Yes. Okay.
Oh, yes. You can't say NIMS. It's like ATM machine, right? Yeah, I get it.
But NIMS feels natural. Anyway, they offer structured output kind of natively.
They're using Outlines too, right? NIM uses Outlines behind the scenes. And TGI, actually, I believe also the structure you get from that does use Outlines under the hood as well.
Yeah, although the NIM is configurable. So you can use Outlines, some fork of Outlines from a while ago called Outlines Fast. Also supports LM format enforcer. And it basically uses the vLLM stuff from under the hood. So you kind of have the same issues with vLLM using an old version of Outlines that's like not representative of current speed. But yeah, big fan of NIM as well. They're very good, super easy to stand up if you haven't done so already. They're really easy to play with.
Amazing. Well, guys, thanks so much for the kind of deep dive into that. I think it's such an interesting technology, how you have this way of automata decoding of what you can sample from the model, and then understanding how it's delivered and packaged with the other kind of inference tools. Awesome. So I'd love to kind of step up the level of abstraction quite a bit and talk about so this paper, it came out kind of arguing against it. It had a great title. It says, "Let me speak freely." Awesome name.
It's an awesome name. I agree with that. I can talk about this paper for too long. I have spent a huge amount of my life dealing with this paper. So "Let Me Speak Freely" is a great title for a troubled paper. So there's a couple things. So anyway, this has been a thorn in our side for a while because this paper got out and claimed structured generation hurts the quality of results, which again, like as I mentioned earlier, that was like my number one thing to establish when I started at dottxt, was to see, is this true? And I really was earnestly back in the day, not coming from a position of I need to prove it's not the case. I was like, I want to know. Like, I want to know if we're hurting output. So I had spent a lot of time, and on some of the evals they used GSM8K, and I had they showed terrible gaps. Not like, it wasn't like they were disagreeing with my results by like, I was getting 81% and they were getting 79 and the default was 80. They were getting like abysmal scores. And I was like, well, this doesn't, I've done a lot of these at this point. I'd beaten GPT-4 on function calling using Phi3 back last summer. I've worked with Hugging Face on a whole bunch of other similar evals. So I had seen a lot of context where structured outputs, like structured generation with outlines, always improves performance. So seeing it hurt is like, was surprising, and seeing it really hurt told me like really damaged results. I knew something was not quite right. So I looked into the paper, and there's the paper is doing a lot, which is actually one of the sort of, I think, challenges that paper has. I'm much more relaxed when talking about this paper now. If you interviewed me in November, it would have been more spicy. But one of the, and actually what's funny is there's a couple of interesting things that I actually liked that this paper, I wish this paper had talked to us before it was published, but it's interesting to engage with it because it helped us talk about structured generation in a couple of neat ways. And one of the interesting things that is kind of actually buried in the paper, which I thought was the interesting thing, is the question of parsing the results from the model, which is actually a huge part of what structured generation is about. And it's not something we talk about a lot. So in the paper, one of the most crucial things they do is when the unstructured model is parsed, when there's no structured generation, well, remind me to talk about that word unstructured, because there's actually a point I want to make on that I always forget. So when they use another model, I believe it's one of the better versions of Claude, they use that to parse the result. So first off, from a practical standpoint, if you're getting better performance while you're using two models, and I didn't have the heart to run this eval because it's not really relevant, but I have a feeling if you would just use Claude in the first place, you would get better performance than if you had used Claude. Just like it just seemed like an interest, but it raises a good point. To the paper's author's credit, the real question there, I thought, which was a genuinely interesting one, is like, okay, you need to get the results out of the model, right? So that means you're going to have to, if you're doing unstructured generation, you're going to have to write some kind of parser. So I think the question of like, how do you parse that is actually a thing that's very much worth talking about. And I actually wish the paper had focused on that, because that's a very good question. Because you think about it with structured generation, for certain tasks where LLMs perform reasonably well, it's about the errors are down to the parsing, right? Like this, like sometimes like in the last letter, it concatenates 4 letters together, and sometimes it would put an arbitrary space. So you could handwrite a parser that will get that. And the question that remains is like, okay, well, how different is, if I spend like an afternoon writing a complex parser, how different now is that than the results of structured output? Because really, in a sense, structured output just means you don't have to write parsers yourself for the output. And asking about whether that's worth it is a very good question. And again, I think that's where the paper is actually the most interesting. One of the things we found is even in their own output, if you just spent like 5 extra minutes looking at the results and wrote a slightly better hand parser, you could actually get a much bigger performance than what they had, like on their own results, using just writing a different parser. And so that was a neat thing to see. But like I said, it's actually a good question, because it's like, okay, well, how much time as an engineer should I write on a parser? What's the point of using an LLM if I have to spend all afternoon handwriting a parser? Should I use another LLM to parse it? Those are actually, I think, very important things to talk about. And then in that context, structured generation solves that problem. So if the end answer is it's easier to write structure in the beginning than it is to write a complex parser, and cheaper than using another model to parse the output, then you should probably still do structured gen. But the other challenge was like and I think this is a legitimately hard thing in this space, is like, how do you measure performance? Everyone runs evals. Evals are really important. I've been writing evals for 3 years now. In all kinds of different contexts, evals are essential, but it's very hard when you say something is better than something else because my eval showed this result and your eval showed that result. Because now you're talking about the skill in writing the prompt and all these other things that you're measuring in the evaluation, including how you parse the answer out, right? You can cheat in these evals if you want for structured gen's behalf, if you just want to make a really terrible, strict parser. In fact, one of the weird things, this is an example of this, in the Berkeley function calling leaderboard, they do not allow things to be counted as floats if they don't have a period and a 0, which I actually think is unfair to the unstructured approach. Like I use that, and I mentioned it in the article and called it out because they use it. So in structured gen, it's easy to conform to these sort of overly strict definitions of what success is. I personally would never ship that as an argument for why structure gen's better, because I feel like that's almost cheating, right? Saying like we have no tolerance for imperfection out of this model, right? It gets back to that parsing question. But the point being is the structure of the eval, the prompts used for the eval are all very messy. And the big thing that they didn't do is they didn't really do apples to apples comparison. So when I do my evals for structure gen, I have the same prompt, right? The same output as expected, and I'm using the same parsing technique, when it makes sense, so that we're really comparing everything, except the difference is one has outlines turned on, one doesn't. In their paper, they really constructed different prompts for these different tasks. And, it's if you're in a rush to get results in a paper and you see good results that are like publishable and you have a great name for the paper, I can kind of understand like the temptation not to dive in and say, hey, could we make the structured part better? And also, they could have done much better with a little bit of effort, in my opinion, which is something that was frustrating with that. But to be fair to other people working on this space, like when is enough? Like if you're trying to do fair comparisons, like, okay, like if I'm comparing structured to unstructured, how much work should I put in the parser to make sure I'm being fair, right? Obviously, I don't want to penalize things for not putting a .0 in a float, but should I be including if the model puts 5 pieces of white space in? Like, I can parse that, should I? So this is actually like a really generic, bigger problem in the publishing space in general, way outside of this paper, is like when you're comparing things with evaluations, all you can really say is, I got it to do this well, right? It's really hard to make negative claims like this doesn't work. All you can say is, hey, I wrote a prompt and it gets these results. You can look at that. But it's very hard to compare things even. Like 2 models might have preferred, early on in my work, I found that when using unstructured, some models completely tank if you ask for JSON out. There was one of the fine tunes for GSM8K, one of the math models. It just, when you said, please return JSON, the model bombed. Again, this is purely without outlines. And another model without outlines, you said return JSON, actually did like way better than its baseline performance. But if you're comparing those, even if you're doing apples to apples, like who's to say? Like the one model actually performs like dramatically better when you're not using JSON than the other model does independent. But like, am I, as the researcher, responsible for sampling the entire space of possible prompts and parsing? It's like, so it's kind of a mess, which does get me back to my larger point on this topic. Is we have been spending a lot of time talking about like, so I've posted a lot of articles about it improves results, and I believe that is true. But it's actually kind of a silly question, because when we talk about structure isn't just JSON. It's not just a particular regex. It's how much structure. Like trivially, all structure is .star, the regex for anything, right? So it's not ever, like there's no such thing as unstructured generation, really, philosophically, right? I'm a very philosophical person. So like, and then the other example I give is, let's say you had to do last letter, right? If my structure, it's got 4 letters in the end. So if my structure only allows 4 numbers, obviously unstructured will perform better, right? It's not possible for my model to succeed because I've defined a structure that's nonsensical. But likewise, if I say it has to be exactly 4 letters, I can guarantee that it will never get parse errors, which removes a whole systemic problem in other ones. So that means that the unstructured can only do at least as good as mine, right? Like that's trivially true as well. So when you think about it from that perspective, then we actually, as like a research community, should not be talking about like, does it hurt performance? It should be how much is good. One concrete example I have of this, actually, it's very interesting to me, is and it's related to the thought control, the chain of thought stuff we were talking about, is in the last letter, what is the task is you get 4 names and you need to concatenate the last letter of each name. And so most of the time the model reasons like this. It says the first name is William, that ends in an M. The second name is Cameron, that ends in an N. The third name is Connor. And it has that format. So you can actually encode all of that thinking, hard code it, except for the name, right? So you actually can have the structure be the first name is, and then you have to say A to Z, whatever, right? And then you can be that rigid. When you do it that rigid, you get better results than unstructured, but actually not as good as if you just let that field be plain and do its own thing. So absolutely, structure generation can hurt performance. Absolutely, structure generation can help performance. And the area we need to understand better, and this is beyond just our team as a community, is what is the right decision? Like, when does this hurt? When can we make guarantees about, okay, this will never be worse than? When can we say this will always be worse than? And it's really about asking that question about what those things are. And so it's in a big picture, as we look at this thing, it's actually not the right question to be asking in the first place. But every time we do it, it works better. So the follow up, even if you're asking the wrong question, we still give the right answer. In that way.
Good button there, Will. I love that.
Yeah, I think that's really interesting. And I love the point you make in the rebuttal that the paper does even show cases where constrained decoding performs better, like with the classification.
Yeah.
Yeah, and then I kind of like a way that I met Cameron online is we had published our structured RAG paper where we were trying to see how we can prompt it to produce JSON, and Cameron responded, "Just use outlines," which is like, well, hey, we haven't discovered outlines yet, but yeah, I guess like what we had found is when you use these prompt optimizers, you can get the JSON from it, but then it's like, why bother when this kind of stuff exists?
And what's interesting, and this is actually one thing I was happy I got to write this paper, is there is rules and best practices to make sure you're getting structured output. So like I walked through it in the write up, but like right off the bat, see if your prompt naturally wants to look like the structured output. Like you should tweak your prompt until you go, oh, I'm getting it. And then another really obvious one is if you have your structure defined as a regex, make sure that regex is in the prompt, right? Like you might have slightly different white space, which is going to lead the model to want to make slightly different output. I hate saying that it wants to, but there's actually things you can do. And that's actually one thing I really like about structured generation. There's actually a lot of very sort of formal, practical things you can do to say, is this a good prompt objectively? Like, is this doing things I think? Does it tend to want to produce the structure I'm looking for anyway? That's a good start. Is the structure I'm asking for in the model itself? That's another good start, right? You can even like debug structure. I've had examples of that where you get like results you don't want, and you can actually make bugs and make tests around that, and like testable, writable code. Like this is cool. So that was the fun part about that too, is really being able to answer rather than just saying like you didn't prompt well, but to say this is how you should prompt for structured generation.
Yeah, and I definitely want to ask some more about that, how you should prompt for structured generation, because I think let me speak freely. I think the intuition that you might have said is because it's trained on language modeling internet text, and so internet text isn't structured like JSON, and that or however it's or like I guess like as we're talking, I'm understanding that there are all sorts of structures.
I'm glad we've already brainwashed you into believing.
I'll probably still be drinking the JSON Kool-Aid for a bit, but like you might think it's like a distribution mismatch. Do you have that perspective at all, or?
Yeah, it's actually really interesting to think about. That's a really like the question of why performance would be worse for cases where it is. I mean, in some of their examples, they didn't even correctly pass the definition of the structure to the model, so there's no way it's just going to guess. But one experiment I've been wanting to run, and I haven't, is sort of like if structure generation hurts performance for a particular definition of structure, so we can ignore this whole philosophical debate of what is structure. The real like what that means is it would have to mean that there's some sort of probabilistic path that is blocked by that structure. People often talk about like what the model wants to do, which I just said that but I think it's a kind of a dangerous way to think, because for example with certain outputs there's just fundamentally wrong tokens. Even if the model really has a tendency to do it, it's still the wrong answer. And like there's no way that going the wrong way will get you to the right place. But the implication is like, okay, like what if we could what if we could visualize all the different branches that this LLM would reasonably take? Then what you would expect if it was getting worse performance, and this is the kind of work I would love to see more of actually, both from us and people outside, is like, okay, we actually looked at all the possible places this model can end up. And the reason why this structure hurts it is it forces it on a different probabilistic path. That would be kind of the stuff I would need to see to start getting. That would be kind of the cool way to kind of explore what's actually happening. And it's something I think we just frankly don't really know a lot about how LLM paths work when they go through sort of this latent token space. I think we actually need to learn a lot more about what this even means. How do you get from one point to another? Why does chain of thought work, right? Like I still hold the belief that it's more like Hamiltonian Monte Carlo. You're doing a warm-up cycle. You're circling the high probability region for the right answer by letting the model take time rather than just go straight there. But that's just like a guess I have. I think there's a lot of work we need to do to understand this.
I think there is a paper to that extent.
Oh, awesome. I
think there is a paper that's like roughly with that gist. But
awesome.
I just to kind of like echo Will is like, we don't really know. We have a deep learning.ai course that came out last week, and in one of the lectures I show how like the probability of tokens being generated as you step through the JSON when you constrain the output. And as soon as you force it to print out curly brace quote, and then name quote colon, it knows what to put there, and the two distributions are aligned basically between the structured and the unstructured. The model, what it would do without outlines and what it would do with outlines. But Will has this bigger point, which is that the entire path is very unknown. Like we don't know how that path looks, whether that forces the model into this like territory it doesn't quite understand and makes it worse. And I don't think there's been like actual serious work about this, which is, if you're a researcher, we would love to hear from you.
Yes.
Because there's so much crazy stuff in here to mine that we just don't, like the coalescence thing. If you go read our coalescence blog post, it's, you can combine the word dog from the tokens D, DO, and DOG.
And also just dog. There's a dog token, right? So
there's a dog token.
Yeah.
But it's not clear the path that you take. If you take all the short tokens, D and then O and then G, is that different probabilistically than just dog? And you don't know the extent to which that path meaningfully changes the total distribution of the sequence.
And it's actually interesting that you mentioned that example, Cameron, because I have an experiment I ran. It's not enough to publish yet, but it shows actually that when we implement this fast forwarding and you're only using the biggest tokens at a time, so you use the fewest to get to your end result, it actually does improve performance. And someone's theory on that was that it's actually, when you think about these models, they're trained on the tokenizer's output, and the tokenizer is actually optimizing for shortest token strings overall. So it's like, that's what the model's trained on. It's not surprising you might get better. But this is like, to Cameron's point, it's like, no, this is something that we need to study as a community. Like, we need to like get out there, which, it's important to mention this when we're talking about this rebuttal paper. This was like a particularly tricky paper because we had like, there was people that didn't necessarily want to sign contracts with us because they saw this paper and were like, this is like making me nervous. And so it's like, this was like, be careful what you say as far as like what can be harmful, but I don't want anyone to think like if you write something bad about a structured gen, we're going to come around and beat you with a stick. Like we actually, I really do want people to have problems with structured gen. I want people to be thoughtful about it. I want them to really try. But if you come across something where you feel like structured gen is getting you weird results, I would actually love to see it and actually work with people on that, because there's so much we don't know about this process that I would love to sort of help everyone. I would love if everyone was participating in sort of understanding this better. There's a lot for us to gain, even for unstructured, like to the point of that token thing. That means that like, maybe you should add a weighted probability to. I actually just thought about this as we're talking, but like if longer tokens tend to result in better things, like the longer, the token itself is a longer string, maybe we should have a bias in our models towards saying, hey, actually you should pick more like what the tokenizer would. This is off the top of my head thing, but like, there's so much room for improvement. Yeah, I'm sorry, Cameron, you go ahead.
There is actually a paper that suggested this, which basically finds that models are biased towards smaller tokens. And I could like totally believe that the smaller tokens are more ambiguous, whereas the longer tokens, if you pick dog, the model understands, there is a word dog, and it is much clearer what the rest of the path should be. So Will is doing some very good work on that research, and I'm like super excited to see.
Yeah, it's really cool to see. Cameron, that paper you're talking about, so you're saying like it says the model, in the case where the token options are dog, DO, and D, it has a tendency to choose D. Is that what you're saying, instead of dog?
It has a tendency to choose D and DO over DOG.
That's interesting, especially because like what I've seen, at least preliminary, is that dog would actually lead to the better outcome, especially if what's cool about structured gen is you can go ahead and actually know that they'll always complete and there's no branching. But like, given what I've seen, if that's a pathology of LLMs, they're choosing smaller tokens, but we know that choosing bigger tokens leads to higher performance. Like there's like these performance wins in this whole community that are like, just someone has to stumble on it and we'll get like better results from these models without any training, which is kind of exciting to me.
Yeah, amazing. I can imagine like picking D is maybe like lower risk, like if you're being criticized on predicting the next token, maybe that has something to do with it. But yeah, anyways, I mean, it's been an amazing overview. So much detail to all this. I learned so much from our conversation. Guys, so one question I kind of like to anchor this podcast with is, maybe stepping outside the details of the, particular things we're working on, and more so kind of talking about the broader space as people working in AI. Like, we just had the release of Llama 4. I think Gemini 2.5, ChatGPT 4, just like with all these latest things. I'm just kind of curious, like for each of you, what your current sentiment is on like some future directions that really excite you the most for AI.
Do you want to go? I can jump on that one if you want.
Yeah.
I mean, I'll try not to rant too long, Cameron.
Okay, here, I'll do you go ahead.
All right. So just to follow on with what I was saying, I'll actually be pretty quick. I actually think the funny thing is we've seen so much progress in the training space that we haven't had enough time to push like the basic architectural questions of like, and I don't mean like architecture like LLM architecture. I mean like the like we're talking about, like structure. Is there a better way to choose tokens? Is there better sampling techniques out there? We haven't done that because the wins that are easiest seem to be letting someone train this giant model. But I am kind of excited for these models to kind of plateau so we can take a breath and start saying, okay, what can we get out of these now? Because they're nowhere near optimal, in my opinion. The actual structure, like when DeepSeek came out, people were like, oh, it's some people were very skeptical of it. But a lot of people in this space, like, I'm not surprised they did better than OpenAI because like there's a lot of room for improvement in these models that are like just, and it doesn't involve more data and more compute. It involves being a little bit more clever with how we build these models and what engineering can be done around them. So that to me personally is where I'm very excited about future stuff, about sort of when people can start hacking at these and really squeezing out, and maybe not small performance. Maybe there's big gains we don't even realize we have right under our nose. So I'll stop talking now, Cameron.
I think the thing I'm very excited about is seeing how people actually build things at scale, right? So that the real reason that you use structure generation is because you can performantly generate the same thing every time. And what that means is you can build giant programs. You can work with, I think the term here is compound AI systems, and you can go very large with these. Like, so for example, you could build an automated hedge fund. And the automated hedge fund has an orchestration agent that dispatches to specialized agents that read through PDFs to extract all this stuff, pass insights back. You could kick off like kind of portfolio analysis stuff where the orchestration agent passes tasks off to various other agents that basically have like access to like specific computational tools. Every single one of those agents can be specialized to their particular task. They're always going to pass back JSON. You can actually build very large programs with this. And most of the things that we've seen people do with like kind of agent systems is they're like less than 10 turns. It's like a very small set of like kind of agent configurations. And I would love to see the scale that people can operate at, because that's ultimately the thing that you get from structure generation is extreme reliability. Your language model just becomes a tool, and speed, because ultimately we can just start giving you free speed through coalescence and through the way that through how we interact with the language model and what overhead we compile and things like that. So I'm really excited about building and seeing what people get up to.
I do like your point, Cameron, about like these certain agent things are a relatively small number of steps. I think one thing that people haven't quite grasped about LLMs and building is that like like when you think about the way code bases work in large tech companies now, like the size of the code and the need to understand it is actually a blocker in sort of efficiently building larger and larger systems. And to what you're describing, Cameron, is like, right, like what happens when there's a billion agents that have long chains of interaction and it's a system we cannot understand, but it allows us to build complexity that works in a scale. This is like a little bit more future thinking, but it really unblocks solving, I think, one of the largest problems in contemporary software, which is like we have billions lines of code bases out there. They're just nightmares to maintain. They're hard to scale and continue growing. And I think these LLM systems potentially unlock a whole new level of software abstraction that we haven't even imagined yet.
Yeah, if I can jump in on this, I've seen like people are jumping on this kind of like agent communication protocols, because now that we know, now that we can force the structured output, let's go ahead and type up like a RPC schema and communicate that way. And I think that gives you an even one more level of speed. And I'm kind of upset with myself that we didn't touch on streaming at all, but that's also something that kind of is unlocked by this. Like when you have these structured outputs, you can just go ahead and start sending it to the next step and all that kind of stuff. And I had mentioned like that we're using outline, so I think I can get away with this sort of self-promotional Weaviate stuff. But we are working on this transformation agent, where kind of one way one cool thing it can do is like if you want to classify, like 10,000 documents, it can do that in like 2 minutes. And I share this vision of like big data, seeing what happens. Especially when you add this like multi-agent component to it, and you add like I don't know if you guys have seen this thing called Persona Hub. I'm kind of obsessed with this thing. It's like it's a billion personas derived from internet scale text, and it's like it kind of helps you think about multi-agent a little bit, because it's like you need kind of like a role, and then you need some way of thinking about scaling roles. If you're going to be doing this, like let's go have a billion personas. But awesome.
This is cool. I just pulled it up. I'll read through this. This is cool.
I remember once when I was at Hex, we had I forget the exact nature of the problem, but the model was not giving us the answer we wanted, and it was giving like a very like strict interpretation of the question. And I remember I just changed the prompt to "You are a very empathetic, thoughtful," and it started working. I didn't test it at scale, so it could have just been luck, but it was it aligned with its sort of personas. I think there's something there, right? So.
Yeah, like the billion persona company managed by one human person.
That's a great point. Exactly. Yeah, this is like there's scale here that like we don't even think about operating in right now, which is potentially possible, which is very cool.
Yeah, amazing. Well, Will and Cameron, thanks so much for joining the Weaviate podcast. This has really been one of those fun conversations. I've learned so much. Just so much information, so many cool nuggets to how this works, and kind of maybe things I think you would find counterintuitive at first, that you're all doing the research and proving how it really is manifested. And that's all just so amazing. Thank you so much.
Oh, thank you, Connor.